Welcome to the 8th lecture for Chemistry 312 Radiochemistry. This lecture we're going to discuss nuclear force, the strong force which keeps the nucleus together, the structure of the nucleus, and models that describe the nucleus. In particular, we're going to talk about the shell model. The readings for this lecture are in Chapter 10 of Nuclear and Radiochemistry and Chapters 5 and 6 of Modern Nuclear Chemistry. This lecture is going to cover the strong force, one of the four fundamental forces of nature. We're also going to introduce a term called isospin. And what the isospin is going to do is relate the neutron and proton to each other as particles without talking about their charge. So we're going to remove the neutral charge from the neutron, the positive charge from the proton. And this way we can discuss the behavior of the nucleons within the strong force. So in other words, how they are held together in the nucleus. We're also going to discuss nuclear potentials. And here are some examples of potentials: the harmonic oscillator, the square well with some rounded edges. These are two potentials that you would have seen elsewhere. We've talked about the harmonic oscillator, something that you would have seen in previous courses. This square well we've talked about a little bit previously in the course. And then if one applies the levels that a nucleus has, so the nucleons can occupy, and then you introduce spin-orbit coupling, what we're going to see is that we get splitting in these levels that reflect magic numbers. And this potential is going to lead us to the shell model. And the shell model, we'll call it the simple shell model, is the focus of this lecture. We're going to use the shell model to determine spin and parity of nucleons. We'll also understand through the shell model, as we discussed in fission, why isotopes tend to go towards doubly magic, so tin 132. And then finally, we're going to end this lecture with another brief example of a model, a Fermi Gas Model. So this would be, the shell model would be for describing a nucleus that it's at a non-excited state, where the Fermi gas describes a nucleus where all the nucleons are at excited states. When we discuss the forces that act upon the nucleus, we've already gone over a few. Well, obviously, there's electromagnetic force, which has to do with charge, protons, for instance. The weak force, neutrino interactions induce beta decay. So in the previous lecture, we talked about beta decay. That's the example of the weak force. And then the strong force is the force which holds the nucleus together. There's pions and then the gluons. So these are just some of the tools that operate within the force. And this is, we also discussed this briefly with the liquid drop model, where we said that adjacent nucleons are strongly attracted to each other. So that's the fundamental basis of the strong force. But if we want to work with that, we need to consider all nucleons as similar. We need to remove the fact that protons are positively charged and neutrons are neutral from this interaction, so that a nucleon can interact with its neighbor regardless of that charge. So we're going to introduce a term called isospin, which we'll describe in a little bit. That is a quantum mechanical term that we can use to describe a neutron and a proton, but remove the charge. And you can think of it as almost a spin up or spin down electron. So you can the similarity would be a neutron and a proton being an electron, one having spin up, one having spin down. They're both electrons, but we describe them differently with some quantum mechanical terms. So these fundamental forces, as we see here, they all exhibit properties, and they have virtual particles that act as force carriers. And the reason that strong force is called strong, well, if we look at the relative strengths, it's by far the strongest. Its range is small. It's about the size of a nucleus. And again, there's particles that are associated with the exchange. As we've already seen, the strong force has a relatively short range. It's on the range of a nucleon. This is one of the reasons why the nucleus is dense. This strong force makes this attractive force in the nucleus so that the nuclear material winds up being extremely dense. There's a force between two nucleons has two components. There's a spherical symmetric force and then an asymmetric force. If one considers a relatively simple nucleus, deuterium, it has a proton and a neutron. These can be parallel spin, so the spin of the neutron and the proton being up. It can also be an anti-parallel in unbound states. So there's some spin properties here that are used to help describe the nucleus. And what we're going to see with the strong force is that the nucleons are considered the same. The charge is removed. So the proton and neutrons within the strong force are going to be treated as the same particles. Fundamentally, one's going to have they're going to have spin differences. As was already stated, the strong force is charge independent. So in this case, pairs of neutrons and protons, or proton-protons should have the same. So somehow, in order to evaluate a charge-independent force, one must remove the Coulomb repulsion from any energy calculations. This can be done by looking at nucleon-nucleon scattering or by mirror nuclei. And here's an example of some mirror nuclei, and these mirror nuclei are isobars with a number of protons in one nuclei equal the number of neutrons in another. So for instance, if we look at 23, we can have sodium 23 and neon 23 as mirror nuclei. As you can imagine, you can evaluate mirror nuclei for only fairly low A. As you go higher in A, you couldn't get a nucleus with more protons than neutrons. So what one could do with this is evaluate energetics, particularly looking at binding energy, and then compensating for the Coulomb energy to try to evaluate a net nuclear binding energy for different nuclei with the same number of total nucleons. And this is shown here. So we have total binding energy, and here's the net Coulomb energy. And as we can see, imagine for something like tritium, there's only one proton, so the Coulomb energy from that would be 0. So for the other nuclei, we have Coulomb energies that are calculated based upon the number of protons in the nuclei. And what this shows, if we take the total binding energy and compare it with the Coulomb energy, we see that the net nuclear binding energy is very similar based upon the total number of nucleons in a given nucleus. And this can be used to show that protons and neutrons are actually two states, can be considered two states of the same particle. And actually this term is called isospin, and it's another parameter that can act to determine reactions based upon the strong nuclear force. And here's some data on isospin. It's a property of a nucleon where the proton can have a spin of 1/2 and the nucleon and the neutron spin of -1/2. Now a nuclear potential is where these nucleons can act together, form a nucleus, and then provide properties that we can observe on this nucleus. We've already talked a little bit about nuclear potentials, but these nuclei can be particles in a potential well. The nuclear forces describe the potentials. The well is small. And we also know that the well can stabilize nucleons. For instance, I can put neutrons into a nuclear potential, and they can remain stable. A free neutron is not stable. It decays. Also, the way I mix nucleons can be stable. For instance, I can put, if I have two protons, that's helium-2, that's an unstable nucleus. Two neutrons is unstable. But if I have a proton and a neutron together, that's deuterium, that's a stable nucleus. And I can also imagine that with A of 3, I can get mixtures of protons and neutrons that are stable. However, 3 protons would be unstable. And this nuclear force within this potential, they act upon the nucleons in a uniform way. So protons that protons have this Coulomb repulsion that act to destabilize the nuclei. So that's why when we get more proton-rich nuclei, we tend to have excess neutrons to help minimize this Coulomb repulsion. So at low A isotopes, these light isotopes, symmetry is favored, where the number of neutrons is approximately equal to the number of protons. As we go higher, this isn't true. In some respects, the potential energy of two nucleons that can be unified in this potential are similar to some chemical bond potential energy functions. So that can actually be used as a model to help describe the behavior of nucleons in a potential well. These concepts and ideas that we've just discussed can actually be applied to the shell model. And we've already kind of hinted at the shell model where there's some experimental evidence. For instance, the ground state spin for all even nuclei is 0 plus. We've discussed magic numbers. So there are certain nuclei or certain states where there's enhanced stability for nuclei, which is pronounced in fission, for instance. There are some systematics on ground state spins for odd mass numbered nuclei, the relationship between magnetic moments and their spins, and some of the properties of ground states of odd mass numbered nuclei can be determined from that odd unpaired nucleon. So it's as if if I have an odd A nuclei, all the nucleons are paired except for one, and that one unpaired single particle provides the properties for the nucleus. That's fundamentally one of the bases of the shell model. One of the other things with the shell model that can be derived is stability of nuclei based upon the number of neutrons and protons. One of the bases of the square well is the potential in which the nucleons sit. A simpler model is to describe the nuclear potential as a square well. A little bit more advanced is the harmonic oscillator, where you get a parabolic shape of the potential. With the harmonic oscillator, we get energy levels that are regularly spaced, shown here. And this is useful really for only low-lying energy levels. If by changing the nuclear potential to a square well with rounded edges, as shown here, we enhance the stability of states near the edge of the nucleus, and we can take these, so we see a lowering of the energies, we see a splitting, and then this splitting goes even further when spin-orbit coupling is applied. And this allows us to see where the magic numbers come from, where we have gaps in the energies between the levels, and these occur at 2, 8, 20, 28, 50, 82, 126. So the shell model is really the square edges and spin-orbit coupling combined. The shell levels are filled based upon their relative energies, and we can define the states by two quantum numbers, n and l, n being a principal quantum number, l being angular momentum. And unlike electrons, nuclear states can have a 1p, a 1d, a 1f, a 1g. So there's a variation in behavior of the shell model with the electron model. What we can do, when we look at these states, we know that there are some states which are degenerate. So we can group some energy levels together. Degenerate states, if I take 2 times n plus l, those with the same numbers, so n and l, so 1s, the n would be 1, the l would be 0. Those states with the same 2n plus l are going to be degenerate, and they'll be grouped together. As an example, if we look at this state here, which is composed of the 2s, and 1d state. 2s, 2 times 2 plus 0 is equal to 4, right? Because the n number is 2, the L number is 0 from s. Where D, a 1d state, the n is 1, the L is 2, where S, P, D, right? So 0, 1, 2, the D is 2. So that's 2 times 1 plus 2 is equal to 4. Those two states are degenerate. We can see the same thing shown here, where we have the 1G, 2D, 3S, where all these equal to 6, and those levels become degenerate. And then when we have spin-orbit coupling interactions, where we can split the angular momentum, where J equals L plus S. As an example for this, we could take the P states, where P is equal to 1. S can either be, the spin is either plus 1/2 or minus 1/2. So the splitting of the P states will either be a 3/2 or a 1/2 state. And this is split into a fourfold degenerate, for instance, in this case, a 1p 3/2, which is shown here, or a twofold degenerate 1p 1/2. And when we say a fourfold degenerate p 3/2, it means I can put 4 nucleons into that state. When I say a twofold degenerate 1/2, it means I can put 2 nucleons into that state. The other thing that we see is the gaps appear at the 1n quantum number. So see a 1s, a 1p, 1d, the gaps are here. 1f, the gap is here. 1g, the gap is between the two 1g orbitals that are formed. Same thing with the 1s, excuse me, the 1h. Even the 1i is at the lower, is at the gap that defines the shell, that defines magic numbers. And we see the 1j here defines the magic number of 184. So from these trends, from the quantum mechanics of the shells, we get a lot of properties that come out with the related to the shell model, particularly the magic numbers and how many nucleons can go into the different orbitals. So the nucleons fill the shells in the shell model from lowest to highest energy. And as we already discussed, an odd A nucleus with one unpaired nucleon will provide the property of the nucleus. It'll basically have some sort of even core with one unpaired nucleon. So whatever state that unpaired nucleon is, the spin of that state will define the spin of the nucleus. The parity will be based upon the orbital angular momentum. So S's, D's, G's, I's have even parity. P's, F's, H's have odd parities. For odd nuclei, where one odd proton and one odd neutron each contribute to the spin and parity, there's no universal rule, and we'll provide some examples of how you can estimate the spin and parity of odd nuclei. Here's our shell model, and here's some of the properties that come out from the shell model. The lowest level is obviously this 1s. It's a s1/2. Since L is 0, J is only equal to the L plus the S, so 0 plus 1/2. It only has the one value. It's shown here. and it contains 2 nucleons. So I can put 2 nucleons into the shell. For the proton side, I can put 2 protons. For the neutron side, I put 2 neutrons. These are the total number, and that's a magic number. So for the shell model, there's a component that is for the neutrons and a component that's for the protons. The next level, we get to the 1p orbital, which splits into the 3/2 and the 1/2, and that's shown here. And we see that for the lower lying 3/2 state, we can put 4 nucleons in. The total amount of nucleons will be 6, so this will be either the 6 protons or 6 neutrons completely filling this shell. The P1/2, I can put 2 nucleons, total number of 8, and this is a gap where 8 winds up being a magic number. So something where I have 8 protons and 8 neutrons, which would describe oxygen-16, should be especially stable from the nuclear component. We see the other shell closures at 20, 28, 50, 82, 126, and then 184. These enhanced abilities from the magic numbers correlate with these gaps in the shells. A few stable nuclei have both closed neutron and proton shells. They're very strongly bound relative to their neighbors. We can also call these doubly magic nuclei, and some examples are listed here. Helium 4, oxygen 16, calcium 40 and 48, lead 208. We can also find doubly closed, doubly magic nuclei that are unstable. Examples are given here, and particularly tin 132 being one of the driving force in the asymmetric fission distribution. So the other aspect of the shell model is here where we can see the number of nucleons, either neutrons or protons, that can fill a given shell, the total amount of nucleons at that given point that fill the shell, and then finally the magic numbers. So as an example, if I have a nucleus with 21 protons and an even number of, say, 20 neutrons, the 21st proton is unpaired. So that'll be, I can put 20 here. The 21st will go into this 1f 7/2 level. So the property of the nucleus will be dictated by that unpaired nucleon in this level. We'll go over some examples. Let's consider lithium 7. 3 protons, 4 neutrons. The proton number is odd, so that's the odd proton is going to define the behavior of the nucleus. And we see that this one unpaired proton, the 3rd proton, lives in this 1p 3/2 level, right? Because I can put 2 protons here, the 3rd one is here. So the spin and parity are based upon this unpaired proton. The spin, if it's 1p 3/2, the spin should be 3/2. The parity is based upon the p state. It has an L value of 1, so the parity, that's odd, so the parity is negative. And as we see, lithium 7 is 3/2 minus, as predicted from the shell model. We see here, this is the state that it occupies, and the 1p 3/2 correlates to 3/2 minus ground state. The excited state, shown here of lithium 7, is 1/2 minus. So the question is, if I have an excited state, I can either take the unpaired proton and excite it, or split one of the paired neutrons and excite one of those. It's much easier for the first excited state just to take the unpaired nucleon and excite it. So the unpaired nucleon would be living in this 1p 3/2. The next state up would be the 1p 1/2 state. We would expect the excited state of lithium-7 to have a spin and parity based upon the 1p 1/2. So the spin would be 1/2. The parity based upon the angular momentum p. It's an odd L, so it should be negative parity. We would predict that it would be 1/2 minus, and that is what we see. The excited state's 1/2 minus, and it correlates with the shell model. We can now consider an example that's a little bit more complex than lithium-7. Let's consider nickel-57, which has 28 protons, 29 neutrons, so that odd 29th neutron, that's going to define the behavior of the nucleus. 28, 29th, that lives in the 2p 3/2 orbital. p 3/2, p has an angular momentum of 1, so negative parity 3/2. We would expect the spin and parity of nickel-57 to be 3/2 minus, and sure enough, the ground state is. So let's consider the excited state. The excited state is 7/2 minus, and if we look here, the 29th neutron is here. If we excite that, we go to a 1f 5/2 level, which is what we see here. So F being negative, 5/2 state. So this also seems to correlate with nickel-57, 28 protons, by the way, magic number. So the nickel-57 is fundamentally one off from being a double magic nucleus. Another example, carbon-13, that's 12 protons, 6 protons, 7 neutron. The 7th neutron is unpaired. That 7th neutron, 6 will fill up here. 7th lives in the 1p 1/2 state. P, as we've already seen in the examples, is a negative parity, 1/2. We would expect the spin and parity of carbon-13 to be 1/2 minus, and it's true. Another example is with vanadium-51. The odd nucleon is the 23rd proton. 20 protons fit into this 1d 3/2, so I can put 3 into the 1f 7/2. 1 is unpaired. So F is also negative, so we would expect vanadium-51 to have a spin and parity of 7/2 minus. Now, the shell model isn't always correct. And as an example, let's consider barium-137. The 81st neutron is unpaired in barium-137. That would leave a hole, right, almost completely filled 82 nucleons. So 81 is the 1h 11/2 state. That would be 11/2 minus. And if you look at the table of the isotopes for barium-137, you see that it is actually 3/2 plus. Now, there are some rules with this. Generally speaking, high spin states generally do not appear as ground states. So it's relatively rare to see something like an 11/2 minus as the ground state. And also, the shell model is based upon a spherical nucleus. If the nucleus is not spherical, then the shell model will not actually predict the state. We'll discuss this in some later slides when we discuss the Nielsen diagrams. We've shown examples of determining the spin and parity for nuclei with one unpaired nucleon. We didn't go over with even nuclei because those are 0+ for the ground state. Now if we have a condition where we have an odd number of protons and an odd number of neutrons, so the spin and parity of the nuclei is determined by the coupling of each unpaired nucleon. One thing that we will see from a trend is that the spin values are integer values. And if we think about if we add two half integer values together, we should get a whole number. So we're going to get these integer spin values. Sometimes the coupling method isn't completely straightforward. One route to determine this is the use of the Nordheim number, where the Nordheim number is the sum of the spin and the orbital angular momentums. If we add the numbers together and the Nordheim number is even, then the spin is the difference between the two numbers, the absolute value of the difference. If the Nordheim number is n, we have two numbers that are possible, either the absolute value of the sum or the absolute value of the difference of the spins of the two states that are occupied by the unpaired nucleons. The parity is from the sum of the angular momentum states, the L states. If that sum is even, it's positive parity, and if it's odd, it's negative parity. We'll go over some examples to show how the Nordheim number works. For an example of the Nordheim number for an odd-odd nucleus, let's consider chlorine 38. Chlorine 38 has 17 protons, 21 neutrons. 17th proton is going to live in this D1D 3/2 state. So the L is D, right? So D is 2, S being 0, P being 1, D being 2. And J, the spin, is 3/2. The 21st neutron, there's 20, 21, is here in the 1F 7/2 state. So L is 3 for the F state, J is 7/2. So the Nordheim number is just 2 plus 2 plus 3/2 plus 3 plus 7/2. That's equal to 10. That's an even number, so the spin is just going to be the absolute value of the difference between 7/2 and 3/2. 7/2 minus 3/2 is 4/2. The spin is 2. The parity is from the L's, so that's 3 and 2. The L is 5, negative parity. The spin is 2. The parity is minus. We expect chlorine 38 to have a spin and parity of 2 minus. If we consider another example of aluminum 26, this is a nucleus with 13 protons and 13 neutrons. So this 1D 5/2 would be filled to 14, so there's a hole, there's one less, there's one missing spot for each the proton and neutron shell. So each particle, unpaired particle, has the spin of 5/2 and an orbital angular momentum of d of 2. So the Nordheim number is 5/2 plus 5/2 plus 2 plus 2. That's equal to 9. That's an odd value. So the spin is going to be the absolute value of the sum or the difference of the spin values. Each spin value is 5/2. So 5/2 plus 5/2 is 5. 5/2 minus 5/2 is 0. We would expect the spin to be either 5 or 0. The parity, each spin state is 2. 2 plus 2 is 4, is even. So the spin's either going to be 0 plus or 5 plus, and the actual value is 5 plus. So here's an example with the odd Nordheim number where you get a choice of answers to evaluate. The main assumption of the shell model is that nuclei are spherical. If one applies a particle model and discusses nuclei as particles in collective motion, one can come up with shapes that are non-spherical. Nuclei can have shapes such as prolate, shown here, or oblate. The prolate, the polar axis is greater than the equatorial diameter. and the oblate is opposite. Evaluation of these axes, so the axes that are defined here, shown here, the prolate nucleus, or the similar ones in the oblate. So the oblate, this X would be larger than the Z, whereas it's opposite for the prolate. We can use that to define the deformation parameter. There's a term shown here, an expansion of this delta term. The delta term is just nothing more than the difference between the axes divided by the root mean square of the axes. So there's a way of evaluating the deformation parameter in terms of the nuclear shapes. This changes the shell model to something that's shown here. This is called a Nielsen diagram. It's an expansion. You can think of it as an expansion of the shell model, where at zero deformation, at that point, we have what we see in the shell model. If we start to go oblate, we get splitting occurring, so the levels change. We can basically now only put 2 nucleons into each of these levels. Or if we go prolate, as shown here, the splitting goes in the opposite direction. The key to this is that I can take a spherical model, and then by having the nuclear shape change from prolate to oblate, I can have a different spin and parity. So for instance, if it's spherical, this state represents the F7/2 state, so I can put 8 nucleons into this state. In a spherical state, as I'm filling up all the odd nucleons, all the unpaired nucleons would have the spin of 7/2, and the parity SPDF, so it would be 7/2 minus. However, if we measure a state that is not 7/2 minus, you can get an idea, you can provide an idea of the deformation of the nucleus. As we see, if it's deformed in an oblate parameter, the spins will be, the higher spins will be of lower energy, and the opposite is true for prolate. This deformation parameter is shown here, and the oblate nucleus will have a negative deformation parameter, and the prolate nucleus will have a positive deformation parameter, and a spherical nucleus, the deformation parameter will be 0. So fundamentally, what we can do from a very simple point of view is use a Nielsen diagram, evaluate what's the measured spin and parity, and if it varies from what we see with the shell model, we can make a prediction that we should see a nucleus of a given either oblate or prolate shape based upon the observed spin. Let's go over some examples for that. So let's consider iodine 127. It's a stable nucleus. Here's the Nielsen diagram for the protons of Z between 50 and 82. For iodine 127, that has 53 protons. That's the unpaired. From the shell model, we would expect the spin to be 7/2, the parity to be plus. The measured spin and parity for iodine 127 is 5/2 plus. So the deformation parameter should show 5/2 with an even L value. If we go to where the nuclei could live, if it's a spherical nuclei, it would be in the 1G 7/2. If it's a prolate nuclei, so a positive deformation parameter, the orbital should be occupied as shown by the blue arrow, and that should be in a 3/2 orbital because it's 53. So the 50 would be the 1 would be what was defined by the 1g 5 halves over here. 51, 52, 53 here. We actually see that for the oblate nuclei, it would be in this 5 halves shell. 50 would be here. 51, 52 would be in the 7 halves. 53 would be in the 5 halves shell. We see that the spin and parity of iodine-127 is 5 halves plus. Based upon this Nielsen diagram, we could say that the nuclear shape, if the spherical is here, oblate is negative deformation parameter, prolate is a positive deformation parameter. The spin of 5 halves for the 53rd proton indicates that this nucleus is deformed with an oblate shape. We can do another example for potassium isotopes. Let's consider odd A potassium isotopes. So the unpaired nucleon is from the proton. Potassium has 19 protons. From the shell model, the 19th proton is living in this 1d 3 half state. So we would expect a spherical potassium isotope to have a spin of 3 halves and a positive parity. If we look at potassium 47, it has a spin of 1 half, positive parity. So we would see that the 19th nucleon could be unpaired in this orbital or in this orbital. If it's 1 half, we know it's in this orbital. Here's the spin of 1 half. This 2, 0, 0, the 2 indicates that it's in the D state, so it's a positive parity. This shows that potassium 47 is an oblate nuclei because it has a negative deformation parameter. Remembering the past lecture on fission, we showed that the fission product distribution is dictated by the shell model. However, we also showed that this asymmetric distribution could be overcome with higher energies. Particularly towards the last slide of the lecture, where we showed the fission of thorium by a proton, where that became symmetric. That shows that there may be need for a model that emphasizes different behavior of nucleons. And the Fermi Gas Model does that. It describes the nucleons as more weakly interacting, and you treat an average behavior of a large number of nucleons on a statistical basis. In this case, the nucleus is taken as a composition of a gas. Imagine that the neutrons and protons are confined to a volume. They act as a gas. So imagine what that really means is that they're at higher energies. So the Fermi model is a reasonable model for nuclei at high energy states. Here's an example of the potential from the Fermi gas model. We see there's a few components. The difference, there's a proton edge shown here in the dashed line, and then a neutron edge, which is more of a step function. There's obviously a difference in the potentials, and that comes into play with the model describing why neutrons tend to be emitted during de-excitation as opposed to protons. This difference in the binding energy, this 8 MeV for a neutron versus a value that would be much larger for a proton, is held within this model. So the Fermi gas model really describes where we have a mixture of neutron and protons, which can be occupied close to 30 MeV. So it's an excited state. And it says that the neutrons are bound by something on the order of 10 MeV, where the protons are bound more. The utilization of this is for energetic reactions in which the shell model no longer fulfills the descriptions of the nucleons in the nucleus.
The Fermi Gas Model has some equations associated with it that describe the momentum of the particles and the nuclear volume. From this, you can rearrange to find the kinetic energy of particles. The real utility of the Fermi Gas Model is for high energy reactions where nucleons go into the excited state. And you can use this to describe nuclear reactions where a compound nucleus is made and neutrons boil off.
Within this lecture, we introduced the strong force as a way to understand how the nucleus is held together, one of the four fundamental forces of nature. We talked about how nucleons, neutrons and protons, within the strong force are charge independent, and we discussed how we introduced the isospin term to describe that. We briefly touched upon nuclear potentials, and really the focus of this lecture was on the shell model. How the shell model can be used to understand spin and parity, how nucleons fill shells very much like electrons fill shells, except there are some differences between the energy numerations and certainly the energy levels. We also talked about how nuclei have shapes, prolate, oblate. We talked about how these shapes change the shell model, and why is that? Because the shell model is based upon a spherical nucleus. If you change the structure of the nucleus from non-spherical, the model split. This is similar to within inorganic chemistry, going from an OH symmetry to something that's no longer OH. Tanami-Sagano diagrams are often used to talk about energy level splittings of electrons. Very similar ideas for the nucleus, where one goes from a shell model to a Nielsen diagram because the nucleus is changing shape. And then we ended the lecture with a brief discussion on another type of model, not much detail, but just so that you know that there are other models available to describe nuclear properties, and it depends upon the state of the nucleus. In the case, the Fermi gas model was used to describe high energy nuclei. We'll conclude this lecture with examples of questions you should be able to answer. An important concept that was discussed is magic numbers. So what are magic numbers? Well, the magic numbers themselves are listed here: 2, 8, 20, 28, 50, 82, 126, and 184. What are the origins of these numbers? Well, they come from the shell model, and it's basically the gaps in the shells. 2, 8, 20, 28, 50, 82, 126, and 184. What are some properties of nuclei or elements with these magic numbers? Well, you tend to get higher stability. For instance, elements that have the number of protons that are equal to the magic numbers, you'll see that there's more stable nuclei or stable isotopes of that element. Tin, Z of 50, is a great example of that. Lead, 82, also has that number. And you'll also see that nuclei that have magic numbers tend to have lower cross sections. Great examples are doubly magic. For instance, lead 208, very low cross section, and isotopes of tin, low cross section for nuclear reactions. Other questions you should be able to answer. Discuss the strong force. One simple question is, what is the strong force? As shown here, the strong force is the force that holds nuclei together. It has a very short range, and it's composed of gluons, which are the particles that are moving between nucleons. How is the strong force evaluated? Well, there's nucleon-nucleon scattering and mirror nuclei. Mirror nuclei are those isobars with numbers of protons in one nuclei equal the number of neutrons in another. These mirror nuclei show that protons and neutrons are two states of the same particle. You're able to ignore charge or Coulomb properties and use this to evaluate how nucleons stick together. And what is a nuclear potential? And as shown here, here's an example of a potential well in which nucleons sit in a nucleus. There's a slight difference between the proton and the neutron potential. That has to do with charge. And this well stabilizes nucleons. And as we know as an example, free neutrons decay. They have a half-life on the order of 14 minutes. However, neutrons can be stable in a nuclear well. Another important concept discussed in this lecture is the use of the shell model to determine spin and parity. And we discussed that the spin and parity is determined by unpaired nucleons in the nucleus. All even nuclei, there are no unpaired nucleons, even number of protons, even number of neutrons. All even nuclei have ground state spin and parity of 0 plus. If we have an example of a nucleus with one unpaired nucleons, we can use the shell model to evaluate what should be the spin and parity. An example, titanium-49, the 27th neutron is the unpaired neutron, and in the shell model that lives here in this shell, which is the F7 halves, so the spin is 7 halves, F is 3, that is odd, so the spin is 7 halves and the parity is minus. If you examine the chart of the nuclides, you'll find that titanium-49 is indeed 7 halves minus. Another example, indium-113, the 49th proton defines this element indium that lives here. It's a G 9 halves. 9 halves is the spin, G is 4, so it's 9 halves plus. If you go to the chart of the nuclides and you see, you look up indium-113, you'll indeed see that spin and parity are 9 halves plus. This also indicates that these nucleons are spherical, since the shell model is used to evaluate and is based on spherical nuclei. Another important concept that was discussed in this lecture are nuclear shapes. So what are some examples of nuclear shapes? Well, as we described the shell model, there's spherical nuclei, but there are also nuclei that deviate from being spheres. One example is a prolate nucleus, and this is that the polar axis is greater than the equatorial axis. The other nuclear shape is an oblate nucleus, in which the polar axis is shorter than the diameter of the equatorial circle. And how does the shell model, how does this change with this deformation going from spherical to either prolate or oblate? Well, we go from using the shell model, which is shown here right along this line. As it changes, we go to our Nielsen diagram, and these states radically change. If you've taken inorganic chemistry, you've seen tsunami-Tugano diagrams, you'll see the same sort of behavior. And what we can see from this is that oblate nuclei are going to tend to lie on this side of the line that defines the spherical nuclei. So on the left side will be oblate, and the prolate will land on the right side.
When you've completed Lecture 8, please comment on the blog and respond to the quiz.